Welcome to Module 8. By now, we have explored finding derivatives of diverse functions through the product rule, the quotient rule, and the chain rule. In this module, we will delve into integrating these rules and applying them in various contexts, including the modeling of periodic behaviors. A significant part of computer graphics, or CGI, involves the simulation of lighting, crucial for achieving realistic effects. One component of this simulation is the variation of perceived light intensity with changes in distance from the light source. Let's just jump right into an example. Consider a CGI model where the perceived light intensity on an object is given by the formula I of d equals 100 minus the quantity 100d over d cubed plus 9 squared. Here d represents the distance from the object to the light source. We want to find the rate at which the light intensity changes as the distance varies. Now we're asked to find the rate at which the light intensity changes, which is just the derivative. So we have I prime of d is equal to 0, the derivative of 100 is 0. And now when we look at the second term, we see that we have a function inside of a function. And so we're going to use the chain rule here. The derivative of the outside function is negative 2 times, and we just write down what's on the inside here. And we subtract the exponent by 1. So that's the derivative of the outside. Now we multiply by the derivative of the inside. And we note that the inside is a quotient. So we're going to have to use the quotient rule here. So we take the derivative of the top term, which is 100, and we multiply that by the denominator here, which is d cubed plus 9. We subtract, and now we have the numerator, which is 100d, times the derivative of the denominator, which is 3d squared. And all of this goes over the denominator squared. So we have d cubed plus 9 quantity squared. And now it's just a matter of cleaning this up some if we can. Negative 2 times, we've got 100d, and in the denominator here we have d cubed plus 9. And now let's look and see what's inside the brackets here. Notice that we have 100 times d cubed, also we have 100 times 9. But on the right-hand side, we have negative 100d times 3d squared. And so that gives us 100d cubed minus 300d cubed, which is negative 200d cubed. And we also have 9 times 100, which gives us 900. In the denominator here, we have d cubed plus 9, and all of that is squared. Well, it looks like we can simplify this a little bit more. We have negative 2 times 100d, and it looks like we can factor out a 100 here, which would leave us with negative 2d cubed plus 9. And in the denominator, we have a d cubed plus 9 times d cubed plus 9 squared, and so when we combine these, we're going to get d cubed plus 9, and all of that is raised to the third power. Well, now if we multiply negative 2 times 100d times 100, we get negative 20,000d times negative 2d cubed plus 9, and all of that is over d cubed plus 9 quantity cubed. Let's look at another example. In a CGI model, light intensity changes when it passes through a medium, such as water or fog. A model for this is I of d equals 300 times the quantity 1 minus d cubed times d to the 1/2. Here d is distance. We want to find the rate at which the light intensity changes when the distance is 0.16 units. I need to find the rate at which the light intensity changes when the distance is 0.16 units, and so I need to find the derivative. Now here we have a constant times a function, so I'm just going to leave the constant here. I'm going to write this 300 down. Now notice that we have a product, and I'll call this first part u and the second part v. And so when we think about the product rule, we know that this will be u prime times v plus u times v prime. Okay, so we have 300 times the derivative of u. Now notice that we're going to have to use the chain rule here. The derivative of the outside will be 3 times 1 minus d. We subtract the exponent by 1 to get 2. And we have to multiply by the derivative of the inside function, which is just negative 1. Now we multiply this by v, which is just d to the 1/2. Okay, now we're going to add this to u, which is 1 minus d cubed times v prime. And so here we're going to get 1/2 comes out in front, and we subtract the exponent by 1 to give us a negative 1/2. Okay, I could do some simplification here, but I'm trying to find this derivative when d is equal to 0.16. So I'm just going to plug this directly into my calculator. And what I find is that the derivative is equal to approximately negative 31.752. The strength of a wireless signal changes according to distance and is modeled by S of d equals 100 plus negative 2d plus 1 over the quantity d squared plus 1 squared. We want to find the distance at which the rate of change in signal strength is 0. We want to find the distance at which the rate of change in signal strength is equal to 0. Now the rate of change is given by the derivative, so we find the derivative first. So we have f prime of d is equal to, now the first term is just going to give us a derivative of 0, so let's concentrate on the second term. Here we have a quotient, so the derivative of the top will be negative 2, and we multiply that by the denominator, which is d squared plus 1 quantity squared. We subtract the top, which is negative 2d plus 1, and now we need the derivative of the bottom. But note that we will have to use the chain rule here. So we get the derivative of the outside function, which is 2 times d squared plus 1 raised to the first, and then we multiply by the derivative of the inside, which is 2d. And all of this goes over the denominator squared. Now note that the denominator is already squared, so when we square that again, we're going to get d squared plus 1 raised to the 4th power. So now look at what we've got. We want to set this derivative equal to 0. But we've got a fraction, and we know that a fraction equals 0 whenever the numerator equals 0. So we're going to start here by just setting the numerator of this thing equal to 0. So we have negative 2 times d squared plus 1 quantity squared. And I think we can do some cleaning up here. Now let's see, we've got a negative times a 2 times a 2d, which gives us negative 4d. And we also have negative 2d plus 1 times d squared plus 1. And we're setting this equal to 0. Remember, d here represents distance, which is always positive. And that means that d squared plus 1 is always going to be positive. So one thing we can do is we can divide both sides of this equation by d squared plus 1. Now note there is also a common factor of negative 2. And so we're going to divide both sides by negative 2 times d squared plus 1. So here in this first term, when we divide by negative 2 times d squared plus 1, we're just left with d squared plus 1. In the second term, negative 4d divided by negative 2 gives us a positive 2d, and we have negative 2d plus 1, and this d squared plus 1 is gone because we divided by it. And on the right-hand side, we still have 0. Well, now we're just going to clean this up some. We have d squared plus 1, and let's multiply 2d into these parentheses to get negative 4d squared plus 2d equals 0. We can combine like terms here, so d squared minus 4d squared is going to give us negative 3d squared plus 2d plus 1 equals 0. Well, now let's see if we can factor this. I'm going to try something like 3d and a negative d. And let's try 1 and 1 with a plus sign in both places. And it looks like if we multiply this out, we get negative 3d squared plus 2d plus 1. And so now we set each of these equal to 0. We get 3d plus 1 equals 0. And we get negative d plus 1 equals 0. And over here, when we solve for d, we're going to get d equals negative 1/3 and d equals 1. Now remember, d represents distance here, so d equals negative 1/3 doesn't make any sense as a solution. Our only solution is d equals 1. These examples illustrate the application of derivative rules in various scenarios, with a focus on combining rules. We now shift our focus to periodic behavior, characterized by activities repeating at consistent intervals. This concept finds numerous applications, such as in predicting traffic patterns on a corporate network or modeling regular maintenance demands. Consider a circle of radius 1. Drawing a line from the origin to a point on the circle creates an angle with the x-axis. We will measure this angle using units called radians. For example, at the point 1, 0, the angle is 0 radians. While halfway around the circle, at the point negative 1, 0, the angle is pi radians, which is approximately 3.14. Completing the full circle to return to 1, 0 results in an angle of 2 pi, which is essentially starting over again at 0 radians, and this demonstrates the periodic behavior. Now there are two functions associated with any angle t, sine of t and cosine of t. The value of sine of t is just the y-coordinate of the point on the circle, and the value of cosine is just the x-coordinate. If we observe the point orbiting around the circle, which means that the angle t is increasing, then we can see how the graph of sine of t traces out. In particular, we see the periodic nature of the graph as t gets larger and larger. Similarly, we see the graph of cosine of t is periodic. So often, when we are trying to model systems that have periodic behavior, we will do so with a function that involves sine or cosine. Let's take a look at one. The daily CPU usage of a server hosting a web app follows a predictable pattern, with usage peaking during specific hours as user activity increases. The usage is modeled by f of t equals 60 plus 40 times sine of 0.262 t. Now we can observe the periodic behavior of the CPU usage over 72 hours, or 3 days. Now, let's think about the derivatives of these types of functions. There's a special relationship between sine and cosine. The derivative of f of t equals sine of t is f prime of t, which equals cosine of t. The derivative of g of t equals cosine t is g prime of t, which equals negative sine of t. Let's consider some further examples. A smartphone brightness adjusts dynamically throughout the day, modeled by b of t equals 50 plus 20 times sine of t minus 15 cosine of t for a 24-hour cycle. Determine whether the brightness is increasing or decreasing at t equals 8 hours. So to determine whether the brightness is increasing or decreasing at t equals 8 hours, we need to find the derivative. So we have b prime of t. Now let's see, we have a constant here, so we know the derivative of that is 0. And when we have a constant times a function, we just write the constant down. We have 20. Now the derivative of sine of t is cosine of t. And we're going to do the same thing here. We'll just write down the negative 15, and the derivative of cosine of t is negative sine of t. And maybe we can clean this up a little bit. It looks like we have 20 times cosine of t. And here we have a negative and another negative, so that makes that plus 15 sine of t. And we want to determine whether the brightness is increasing or decreasing at t equals 8. So we need to plug 8 into this derivative. So we have b prime of 8 equals 20 times cosine of 8 plus 15 times sine of 8. Now I'm just going to do this in my calculator. And first I'm going to make sure my calculator is in radian mode, and I'll do this by pressing mode. But then I'm just going to plug 8 into this function, and we get approximately 11.93. In a CGI scene, a magical artifact emits a pulsating glow. The light intensity, which changes over time to create a captivating visual effect, is modeled by f of t equals 50 plus 25 times cosine of 0.628 t. Here t is time in seconds. Find the rate at which the light intensity is changing at t equals 18 seconds. So we want to find the rate at which the light intensity is changing at t equals 18 seconds. That means we need to find the derivative. So we have f prime of t. Now from this first term, we just get a derivative of 0. And let's go ahead and write down our 25. Now notice here that we have a function inside of another function. So the chain rule tells us to take the derivative of the outside function and multiply it by the derivative of the inside function. The derivative of the outside function is negative sine 0.628t. And the inside function here is 0.628t, so the derivative there is just 0.628. So let's clean this up just a little bit. Here we've got 25 times a negative times 0.628. So it looks like that gives us negative 15.7 times sine of 0.628t. Now we need to find this derivative at t equals 18 seconds. So we need f prime of 18, which is negative 15.7 times sine of 0.628 times 18. When we plug this into the calculator, we find this is approximately 14.96. In a CGI scene, the camera is approaching a magical artifact with a pulsating glow. As the camera moves closer, the pulsating becomes more intense. The light intensity is modeled by h of d equals 60 plus d times sine of 0.2d, where d represents the distance between the camera and the object. Is the light intensity increasing or decreasing when d equals 10? So I need to find the derivative. And we see here that in the first term, that's just a constant, so that will be just a derivative of 0. But the second term is a product. So let's call the first part u, and the second part of the product v. And we know that we'll use the product rule, u prime v plus uv prime. So we get h prime of d equals 0 from the first term, and u prime, that would just give us 1. V is just sine of 0.2d, plus, now we have u, which is d, and now we do v prime. And we see here that we have a function inside of another function, and the derivative of the outside function is cosine 0.2d, and we multiply that by the derivative of the inside function, which is just 0.2. Now let's clean this up a little bit. Looks like what we have here is sine of 0.2d, and we've got 0.2 times d, and cosine 0.2d. And that's our derivative. Now we want to know whether the light intensity is increasing or decreasing when d equals 10. So we need to find h prime of 10. So we have sine of 0.2 times 10. And 0.2 times 10 will just be 2. And again, here we get 2 and cosine of 2. And at this point, we can just plug this straight into the calculator to see what we get. It's approximately equal to 0.077. So we see that the light intensity is increasing because this is positive, though not by very much. In this module, we've explored how to combine rules to find derivatives that can be applied in various scenarios, from CGI lighting to smartphone technology. We've also delved into modeling periodic behavior. It's sometimes said that the beauty of calculus lies in its ability to model and predict the world around us. We've come a long way, but there are more topics to explore in future lessons.